very good evening. Welcome to this online tutorial of electric circuit analysis on alternate current. For this course, it will be necessary to have previous knowledge on electric circuit analysis on direct current or DC, and also to know how to work with complex numbers. We will see why. So in this very first video, we are going to talk about the basics of electric circuit analysis. And to start, we will mention the difference that exists between the electric circuit with DC current and the electric circuit with an alternate current, an AC current. So on DC, we will see that the circuits are fed by batteries, right? We will see that these are the representation of a voltage source, for example, right? These sources have the property of not changing their value in time. What does that mean? It means that if I graph voltage versus time, and I say that any of these sources supplies 4 volts, then their value, its value will be constant. So the function that actually describes this curve will be a straight line with slope 0 and with the volts units. Okay? So what happens on AC current? On AC current, the circuit will be fed by actually plug them in on the power supply. Okay? So the representation of a voltage source in this case will have a little difference, that it will be a wave here between the minus and the plus. So the difference between this voltage source and this other voltage source will be that if again I graph voltage versus time, on AC current the value will be not constant. Okay? So, for example, if I put a maximum value of 4 and a minimum value of -4, then the function that actually describes the movement, well, this curve, it will be no longer a straight line. It will be a sinusoidal form, right? Or a cosine. So, for example, I will put 4 sine of 2t volts. Okay? I'm not saying that this is the function that is graphed here, but I'm just exemplifying what a function like that will describe. Okay? So it's important to see that, well, as we move on, we will see what does this number mean, what does this number mean, but it's important to see that everything is linked together. Okay? So these functions are used to describe, for example, the movement of a wave, the movement of a spring, any system that develops a simple harmonic movement could be described with these functions. So a way to work with this function is getting them on a phasor domain. Okay? So a phasor is actually a graphical representation on a polar plane. Okay? So in this polar plane we have this real part on the x-axis and imaginary part on the y-axis. Right? So if we draw here a vector, this is actually our phasor that will be having an angle and a magnitude. Okay? So on DC current we were working on time intervals, right? On the time domain. But in this case, on alternate current, as we're working with signals, we are going to be working on the frequency domain. That's why we use phasor. And as we are using phasor, we will be working with complex numbers. Okay? So, just to review the basics of complex numbers, well, if I name here my complex number 0 sub 1, we need to remember that this number will have a real part named A in this case and an imaginary part named B, always accompanied with I. Okay, well, this is actually a J, but in this course it's important for me to say that I will be using j instead of y to work with complex numbers because I want to avoid any confusion with the current representation and, well, let's move on. If we put another complex number here named zeta sub 2 with a real part named minus a sub 1 and an imaginary part named minus b sub 1 I, well, what would we do if we want to add them, or the summation of these two numbers? Well, it'll only be the real part with the real part, the imaginary part with the imaginary part. For the subtraction is the same thing. For the multiplication of two complex numbers, we will apply the distribute property, right? And, well, we need to take into account that I is actually the definition of y, of what does minus 1, the square root of minus 1 means, okay? This is not a letter, this is a symbol, okay, that comes from the Greeks. So if we put I squared, it will mean minus 1. If we put I to the third, it will be minus I. It will be I to the fourth, it will be 1. And on, okay? So when we want to multiply two complex numbers, if we take into account these four values, then we will not have any problem, okay? The division of two complex numbers, well, it's important to review the theory because, for example, in this concrete example, if we want to divide zeta 1 over zeta 2, what we are actually doing is multiplying zeta 1 times the inverse of zeta 2, okay? So this is very logical because if we want to, for example, divide 1 over 3, then what we are actually doing is multiplying 1 times the inverse of 3, right? But we need to remember what does the inverse of a complex number is. So the inverse, in this case, of a complex number, in this case zeta 2, will be the conjugated of zeta 2 that is also represented like this, okay, over the magnitude of zeta 2 squared, right? So, having said that, it's important to remember how to obtain the magnitude of a complex number. For example, if we want to take the magnitude of zeta 1, we only have to raise the real part to the power of 2 and raise the coefficient of the imaginary part to the power 2, and then the square root of all of that will have our magnitude. I said that the coefficient will be squared. Why I'm saying that? Because it's a common mistake that you include y in here. This is wrong. We are only taking the coefficient, right? So in the case of zeta 2, we will have a sub 1 squared plus minus b sub 1 squared, the square root of all that, and we have the magnitude of zeta 2. So in this concrete example, we will see that the multiplication of these two will be a plus bi times minus a sub 1, because we are going to take the conjugated. Let's remember that the conjugated is only, we can obtain the conjugated only changing the sign of the imaginary part, right? So divided by the magnitude of zeta 2 squared. So that means that if the magnitude of this, if I square this, then I will have minus a sub 1 squared plus minus b sub 1 squared. So I am not follow this procedure because I only want to exemplify what the division is, but you can do it at home. And well, just to finish this first video, complex numbers will be represented in a rectangular way or in a polar way. This is our rectangular way, okay? The real part and the imaginary part. But if we want to take, for example, the polar way, we will have to write the magnitude of the number and later on the angle of the same number. We will know how to take the magnitude, but let's remember how to take the angle. The angle, for example, of theta 1 will be the inverse tangent of B over A in this case. It's important to say that this angle, we need to localize this angle. Why is that? Because, for example, if I draw here my plane, where is theta 1? A is positive, the real part is positive, and the imaginary part is positive. So, real part A, imaginary part B, Y. Then, if I do this, I'm taking this angle. But, for example, in the case of theta 2, if I want to obtain the angle of theta 2, okay, let's put it this way. And if I do the same thing as in theta 1, then this result will be the complementary angle, right? Because a sub 1 is negative, b sub 1 is negative. What I'm taking actually is taking this angle. But for other purposes, the real angle, well, the correct angle is this one. So for taking the action, this angle, well, it's only need to add 180 degrees, right? And that is how I take this angle. So it's important to know this stuff to start working with this circuit analysis on alternating current on the